Okay, we're going to look at another application for integration that arises in physics, which is called work, finding how much work is done. Definition of work is a product of force and the distance. So, for example, if there's a block, you're applying a certain force to push this, and you push it from, say, you apply a force of B, and you push it from this place to another place, and it's a distance x, then the work done is going to be Fx. And force is given by mass times acceleration. The units force are, its mass is kilogram, acceleration is meter per second squared. So this whole thing is called Newton. So work is force times distance, so that's going to be Newton that we just saw. And for distance you have meter, and that's called joule. So let's do a simple example first. How much work is done in lifting a 1.2 kilogram book off the floor and put it on a desk that is? So here's the floor, here's the desk, here's the book. Okay, so this is 0.7 meters. Use acceleration. So G is acceleration due to gravity. Okay, so basically what's happening is we're always pulled down by this much force that keeps us tethered to the ground. So in some sense, we're always falling, right? It's just that we fall to the floor and then we stopped. If there was no floor, we just keep on falling forever. So here, first we need the force. Now the force is mass times acceleration, which in this case is G. And that's 1.2 times 9.8. Once you have force, our work done is going to be 1.2 times 9.8 times the distance, which is 0.7 meters. Which you can use a calculator to evaluate, and second it should come out to be 1.2 times 9.8 times 0.7. That's 8.232 joule. Yeah, it's joule because we're working in SI unit. The second one says, what about a 20-pound weight 6 feet off the ground? Now the only thing here is you have to change this into kilograms, and you have to change 6 feet into meters, right? That's why I'm going to leave part B for you, because the only thing you have to do there, which is new as compared to part A, is convert it to SI unit. So where does calculus come in? The force function was constant in the previous one, right? The force that is applied to us due to the gravity is considered constant. What happens if that is no longer the case? So say we can draw a graph of the force and the distance. An object moves from A to B, and a variable force f of x is applied on it. Now calculating work done, it actually amounts to finding the area under this curve, or finding the integral A to B of f of x. Why? If I break into certain rectangles, if I break into small enough rectangles, I can say that this function is constant, basically. And then, if that is the force and that is the distance, then f times x, which is the area of this rectangle, is the work done. Let's say there's a particle located x distance from the origin. Here's the origin. And there's a particle here at a distance so there's a particle located x distance from the origin, and it experiences a force of x squared plus 2x pounds. Okay, now again, we have to use a small conversion factor of changing this force into how much work done in moving from x equals 1 to x equals 3. Now we can work in this particular unit of pounds because we also don't know what these units of distances are. So in general, the integration method works if you are in whatever unit you are in. So the work done in this case is going to be x squared plus 2x dx from 1 to 3. And that's 1/3 of 2 cubed minus 1 plus 2 halves of 3 squared minus 1. That's 26 over 3 plus 8, which comes out to 50 over 3 units. Using units here because we have not been told what units x is being measured in, and then the forces are also not in the correct unit. We'll look at another example in the next video.